Hello students, welcome to Alphos e-learning. This is session 65. In previous session, we was learned that chemical properties of phenols, reactions which involves cleavage of OH bond, reactions which involves cleavage of CO bond. That reaction takes place at high temperature and in presence of Lewis acid catalyst. And also we learn reactions which involves benzene nuclei, that means what we call electrophilic substitution reactions. And particularly nitration concept is important. With concentrated nitric acid, the phenol undergoes oxidation. Phenol undergoes oxidation rather than nitro product, means orthonitrophenol and paranitrophenol. So phenol undergoes oxidation with concentrated nitric acid. What product we are going to get? Always we are going to mention that it undergoes oxidation, but what product you are getting? You are getting quinone, para-benzoquinone. This is the product what we are getting with concentrated nitric acid. And with dilute nitric acid you are getting orthonitrophenol and paranitrophenol, but you are not getting good yield. You are getting poor yield with dilute nitric acid. If you want to get good yield of nitrophenols, then better to perform first sulfonation followed by nitration, then ipso substitution we was learned. Now let us see named reactions which involves in phenol. Named reaction which involves in phenol. Before going to discuss that named reaction, let us see one reaction. Phenols upon undergoes condensation with aldehydes. Phenols undergoes condensation with aldehydes. We are getting products. What products we are getting? Let us see. So condensation reaction. Condensation with aldehydes. Phenols undergoes condensation with aldehydes, either in acid or base medium. R C double bond OH. Either in acid or base medium. Then we are getting product. OH, CH, OHR in ortho position, and OH, CH, OHR in para position. So what's that here? Substitution only takes place now. You mentioned that condensation. So far substitution only. Further there involves in condensation. Let us see that condensation reaction. We are getting bakelite is the product. Bakelite is nothing but a phenol formaldehyde resin. I hope you got the point. If instead of any other aldehyde, if formaldehyde is participated in the reaction, instead of any other aldehyde, if formaldehyde is participated in the reaction, then that reaction what we call phenol formaldehyde resin. Also that reaction what we call Lander-Manasse reaction. As I mentioned that phenol undergoes condensation with aldehydes. Phenol aldehydes undergoes condensation, you are getting products. And if that aldehyde is formaldehyde, then that reaction what we call Lander-Manasse reaction. Let us see Lander-Manasse reaction what happened in acid and base. Now phenols upon reaction with formaldehyde. HCOOH in presence of either acid or base, either acid medium or base medium, then we are getting product here OH, CH2OH. This is what we call alcohol, benzyl alcohol, ortho-hydroxybenzyl alcohol, para-hydroxybenzyl alcohol, ortho-hydroxybenzyl alcohol and para-hydroxybenzyl alcohol. Frankly, the reaction is not going to stop here. This reaction will go further, and before going to learn how further reaction proceeds, first let us learn how these two products we are going to get and what mechanism generally involved. Have a look. First, in acid medium, HCOOH, in acid medium, formaldehyde with H plus, it gets protonation OH plus H, and this one further reacts with CH2OH plus. Now this is electrophile. CH2OH will be electrophile. In such a case, as we know, phenolic OH group is reactivating. It donates electron to the ring. It donates electron to the ring, and further it makes ortho and para positions are electron rich. Now this electron rich ortho and para positions, upon ortho and para positions, electrophile CH2OH plus has to come and attack upon either of these two positions. As a result, we are getting product here OH and CH2OH, and further para position also consists CH2OH. Here I am not going to write in detail mechanism, but you need to practice yourself. Here I am not going to discuss in detail mechanism, but you need to practice yourself. Don't forget that. Here I am writing direct products. And if the reaction performs in base medium, in case of base medium, first that mechanism is in acid medium. This mechanism is in acid medium. And in base medium, first phenol converts into phenoxide ion. Phenol converts into phenoxide ion. Now this phenoxide ion, as just now we learned that this phenoxide ion activates ring much more. Hence, this phenoxide ion gives electron pair to the ring, and it makes ortho and para positions are more electron rich. And this ortho and para positions are more electron rich here. We are getting structure like this, and upon this one involved in resonance, we are getting negative charge in para position like this. We are getting negative charge in para position like this. Now, this one upon further reaction, further involves in resonance structure, we are getting one more like this. So ortho and para positions are electron rich. Now either ortho or para position is going to involve in the reaction with formaldehyde. So let us write here with HC double bond OH, and this negative charge has to come and attack upon carbonyl carbon. Resultant we are getting C double bond O, and there will be new bond formation between this carbon O minus H and H, and this hydrogen CH bond is going to break in presence of acid medium. Protonation from solvent, L converts into OH and CH2OH. So just similar to this one, if para position containing negative charge involved in reaction with formaldehyde, then we are getting one more product, that is para hydroxybenzyl alcohol. So in lateral Manson reaction, phenol upon reaction with formaldehyde, we are getting first ortho hydroxy and para hydroxybenzyl alcohols. Now these ortho hydroxy and para hydroxybenzyl alcohols are not here. Reaction not stopped. Further, how reaction performs? Let us see. So in lateral Manson reaction, if we are using excess of formaldehyde, when we are using excess of formaldehyde, there is a possibility in both ortho and para. In both ortho and para. Gas substitution for both ortho and para positions both happens. Now, here so far we discussed three type of products. One is only ortho hydroxybenzyl alcohol and para hydroxybenzyl alcohol. Ortho para, both position benzyl alcohols. Now condensation means two or more molecules combine to form large molecule without elimination of small molecules like water or HCl. See here what happens. I am going to consider OH and CH2OH. Now this one upon reaction with one more OH, CH2OH. So here condensation takes place if then resultant product what we are getting here. We are getting OH, CH2, CH2. If this chain extends like this, Then resultant what we are getting here? Polymer, linear polymer. This is what we call linear polymer. And now, if para-hydroxy benzyl alcohol is involved, OH, ring containing CH2OH, this one upon reaction with OH and CH2OH. See here, this one is para and this one is para. If here condensation takes place, removal of water molecule, then we are getting product like this CH2, and this CH2 attached to ortho position here OH, CH2OH. Further it continues, and if both are there, means ortho and para both are there, in such a case we are getting cross links. We are getting cross links and here further so in between these two isomers we are getting between bridges, this CH2 bridges, and in between these two rings the CH2 bridges. So there are so many types of polymerization reactions are possible in this. Resultant we are getting products Novolac and Bakelite. These two are phenol formaldehyde resins. Resin also just like polymer, but in polymer thousands lakhs of molecules are involving, whereas in resinification or resin formation few molecules, means 10 to hundreds of molecules are there. So resin also nothing but a polymer. Here in polymer thousands of molecules are involved. In resinification only hundreds of molecules are going to take part. Here you are getting linear polymer like this in condensation. Along with this linear, cross links also possible. So both are possible. Linear polymer and cross link polymers are called Novolac and Bakelite. Students, in Langer-Manson reaction, condensation product you are getting, for the linear and cross-linked polymers you are getting. That depending upon excess amount of phenol or excess amount of formaldehyde. Now let us see freeze rearrangement. Freeze rearrangement, previously we discussed that phenol upon reaction with acetic anhydride, CH3CO taken to ISO in presence of constant sulfuric acid which acts as dehydrating agent. Then we learn that O C double bond O CH3. This is what we call phenolic esters. Nothing but phenyl acetate or phenyl ethanate. The reaction we already learned in previous session. But why you are discussing again here? Now let us see. If you observe with common sense, why O acylation? Nothing but in this reaction, exactly what happened if you observe? See the mechanism here. CH3, C double bond O, O, C double bond O, CH3. This one upon acidification. Then what we are getting? CH3, C double bond O, O, C double bond O, CH3H plus. Here these electrons will come here like this, and we are getting CH3, C double bond O plus, acylinium carbocation which is more stable, and this acylinium carbocation has to come and attack upon phenol. Now, in order to accommodate that, phenolic oxygen is going to take part in the reaction. And this oxygen reacts with the acylinium carbocation. Means oxygen is going to donate electron pair to acylinium carbocation. In such a case, we are getting phenolic esters. Fine. Now, if you observe with common sense, we are getting one more doubt. Sir, you mentioned that this oxygen containing lone pair is involved in resonance with benzene ring. It involves in delocalization. In such a case, ortho and para position gets activated, isn't it? So if it is so, this ortho and para position containing carbon may participate in the reaction. Resultant, the same acylation takes place in ortho and para position. In such a case, we are getting different products. And moreover, here if acylation takes place at oxygen, then what we call the O acylation means oxygen is participating in acylation. If acylation takes place at carbon of ortho and para position, that is called C acylation. So here CC bond formation takes place. The earlier case OC bond formation takes place. If this carbon is involved, CC bond formation. If oxygen is involved, OC bond formation takes place. And previously, so many reactions we learned that compared to OC bond, the CC bond is more strong. So if it is so, why you are saying this reaction? Yes, here reaction is not going to stop here. After O acylation, the acylium carbocation goes to either ortho or para product. That rearrangement what we call freeze rearrangement. This freeze rearrangement takes place in presence of anhydrous AlCl3 means Lewis acid catalyst. Now let us see in freeze rearrangement how reaction proceeds. Say phenolic esters OC double bond OCH3. This one upon reaction with anhydrous AlCl3 Lewis acid catalyst, and this oxygen is going to get advantage to vacant orbital of aluminium, and resultant PHO, and here AlCl3. Here aluminium gets negative charge and oxygen base positive charge. Here C double bond OCH3. Now whenever oxygen base positive charge, immediately there will be bond breaking. Here this OC bond pair of electrons shifted towards oxygen. The resultant we are getting benzene ring. Containing oxygen with the AlCl3 negative charge. And in addition to that, here what left? CH3 C double bond O plus. This CH3 C double bond O plus acylium carbocation is more stable because of oxygen containing group that is involved in resonance with the positive charge. Now the same positive charge has to come and attack in ortho and para position. Resultant, we are getting product here O AlCl3 minus, and in order to accommodate that, this positive charge has to come and attack upon this one. For that, this oxygen is going to get advantage, and this C class has to come and attack upon this one. Resultant, we are getting product here O double bond O plus AlCl3 minus, and what we are getting here C double bond O CH3, and here one hydrogen also there. So whenever here O plus Al minus Cl3, then it get back its electrons, and here it comes to C double bond O, and this C double bond O by involving in Harper conjugation, it converts into phenol, and AlCl3 comes out because of its catalyst. In first step it's participated, in last step it has to come out, and there will be new bond formation, double bond formation here. Earlier means it retains its aromaticity, then we are getting product this one. Similarly, if the same acylium carbocation come and attack in para position of phenol, then in such a case we are getting product para product OH and C double bond O CH3. At low temperature, para product is measured. At low temperature, para product is measured. At high temperature, ortho product is measured. Why, sir? And in previous session also we discussed that. So at low temperature one product, at high temperature one product, and compared to that we are getting here reverse phenomena. Yes. Here, one if you observe here, OAlCl3 minus this is bulky group. And if acylium carbocation has to come and attack upon this one, it has to face some hindrance. In order to overcome that hindrance, it requires some energy. So when you provide energy, that means when we are providing heat energy, then it can overcome that hindrance, and further it makes ortho product as major. And in absence of such heat, at low temperature like around 60 degrees Celsius temperature, it preferably attacks in para position rather than in ortho position, because in para position hindrance is much less. That's why we are getting para product is measure at low temperature, and ortho product is ortho product is measured at high temperature. And at high temperature, which product is measured? That product what we call thermodynamic product. And low temperature, which product is measured? That product what we call kinetic product. So students, next reaction is cold-base reaction or cold-base Smith reaction. Cold-base reaction or cold-base Smith reaction. In cold-base or cold-base Smith reaction, phenol upon reaction with sodium hydroxide, we are getting sodium phenoxide. This sodium phenoxide upon reaction with the carbon dioxide at 4 to 6 atmosphere pressure, we are getting ortho-hydroxybenzoic acid or salicylic acid. Let us see the reaction. Phenol upon reaction with sodium hydroxide, we are getting sodium phenoxide. So O minus we are getting Na plus, and we know that this O minus oxygen is electron rich. Now this oxygen containing group pair is involved in delocalization, and it makes a ring is electron rich, means it activates ring, and ultimately we are getting negative charge in ortho and para position. Now this one upon treatment with CO2 at 4 to 6 atmosphere pressure, this O minus has to come and attack upon carbon. Then we are getting product here O, C double bond O minus and Na plus. Here oxygen carbon bond formation, regarding this you know very well, compared to this one CC bond formation is more strong, and this one undergoes rearrangement. Compared to this one, it undergoes rearrangement. Or you can also add like this: whenever these electrons are involved here, and this pi electrons are shifted towards this carbon, and now this carbon is going to take part in the reaction, and it reacts upon this carbon dioxide carbon. Here, since oxygen both are more electronegative oxidants, these are pulling electron towards itself. Resultant carbon acquires positive charge. Here carbon acquires positive charge. Upon partially positive charge in carbon, this carbon has to come and attack upon this one. Resultant, we are getting product directly here. O minus. Here O minus involved in resonance, that's why double bond O. Now this carbon is going to take part in the reaction. C double bond O minus. Now, in order to retain its aromaticity, this keto form is converted into enol form. Resultant, we are getting OH, and here C double bond O minus, which upon acidification we are getting ortho hydroxy benzoic acid, also called salicylic acid. So students, once again, phenol upon reaction with sodium hydroxide, we are getting sodium phenoxide. In sodium phenoxide, oxygen is going to be a negative charge, and now it can attack upon any positive charge. In other words, this negative charge is going to take part in delocalization. Resultant ortho and para carbons are more electron rich. Now, here, if O minus directly involves in the reaction, we are adding OC double bond O minus Na plus, and OC bond relatively weak compared to CC bond, and even though formation of this one, this undergoes rearrangement at a little temperature, and we are getting ortho product. And if we are increasing more temperature, that means at high temperature we can say, para product is measured. Para product is measured. At low temperature, ortho product is measured. Again, old convention. At a high temperature, para product is measured, means para product is thermodynamic product, and at low temperature, ortho product is measured, means ortho product is kinetic product. So the next reaction is Gattermann reaction. Gattermann reaction is nothing but hydroformylation. So in hydroformylation, what reactants are involved? Let us see. Phenol upon reaction with HCl, liquid hydrogen cyanide, HCl and HCl in presence of anhydrous AlCl3. Phenol upon reaction with HCl and anhydrous AlCl3, we we are getting para-hydroxybenzaldehyde. Para-hydroxybenzaldehyde means hydroformylation takes place in para position. So how the mechanism possible here? Let us see. First HCl upon reaction with HCl. Here we are getting here nitrogen has a more negative charge and carbon takes positive charge. Here H plus and Cl minus. Resultant we are getting HCCl double bond NH2. This one here chlorine has 3 lone pairs. Now this one upon reaction with AlCl3, it takes at Cl minus and converts into AlCl4 minus, and what remains here is Hc plus double bond NH2. Now it acts as electrophile. Now here OH phenol group, phenolic OH, it activates the ring and it makes ortho and para positions are more electron rich. This one upon reaction with Hc double bond NH2 plus here para position carbon come and attack upon this one. Resultant we are getting OH and product directly I am going to write here Hc double bond NH2, which upon hydrolysis C and double bond is going to break here, and we are getting oxygen here and hydrogen here. So product what we are getting here is C double bond OH plus NH3. First hydroformylation, determined reaction nothing but phenol undergoes hydroformylation. For that HCl and HCl elements of AlCl3, HCl reacts with HCl and we are getting HCCl and H2, and from this Cl minus taken by AlCl3 and leaves electrophile Hc plus double bond NH2. And now this acts as electrophile, it has to come and attack in ortho or para position, and obviously in ortho position hindrance is there, so para position is more free position, and it come and attack upon para position, you are getting para product. And during hydrolysis, simply remember that by breaking two bonds, two OH groups has to come and attach to carbon, and the hydrogen comes to nitrogen. So NH3 comes out of two OH groups, water molecule is made out, and what remains here? C double bond OH. So para formylation. Students, next chemical reaction is a much familiar reaction, and that was already learned in chloroform Raymond-Hammond reaction. Raymond-Hammond reaction is phenol upon reaction with chloroform in presence of alkali. Phenol upon reaction with chloroform in presence of alkali, either KOH or NaOH. We are getting ortho-hydroxybenzaldehyde or salicylaldehyde. Ortho-hydroxybenzaldehyde or salicylaldehyde, KCl plus H2O. Now let us see the mechanism. What intermediates are involved in this reaction? First CHCl3 upon reaction with OH minus, it abstracts proton and leaves CCl3 minus, and from this CCl3 minus, Cl minus reported, and what we are getting is dichlorocarbene. Dichlorocarbene here upon reaction involves reaction with the phenol, and we know that in phenol oxygen lone pair is involved in delocalization, and resultant it makes ortho and para positions are electron rich, and right now dichlorocarbene is neutral electron deficient species. Now it acts as electrophile, and this electrophilic carbene attached to ortho position, and what we are getting here is OH. Because of here this reaction takes place in base medium, that's why phenoxide ion is going to take part in the reaction, and we are getting here like this negative charge, and upon this negative charge CCl2 has to come and attack. Resultant we are getting there will be two bond formation between carbon and carbon, and this carbon gets negative charge here hydrogen. Now in order to retain its aromaticity, here we are getting OH and CCl2 minus. This one abstracts proton from solvent H2O. Here OH minus remains, and we are getting CHCl2 in ortho position. And which upon hydrolysis, these two Cl groups are going to be replaced by two OH groups by substitution, and further we are getting ortho-hydroxybenzaldehyde. Instead of chloroform, if we are using carbon tetrachloride, and from carbon tetrachloride you are getting product. You are getting product orthohydroxybenzoic acid, that what we call salicylic acid. Right now we are getting salicylaldehyde. Right now we are getting salicylaldehyde orthohydroxybenzoic. But if we are using CCl4, then we will get salicylic acid. Write that mechanism. In previous session already we learned. Now write the mechanism with CCl4. So students, in oxidation of phenols, we learned that with concentrated nitric acid we are getting paraquinone, parabenzoquinone. Not only with concentrated nitric acid, with any strong oxidizing agent like KMnO4, potassium dichromate, sodium dichromate, anyone, we are getting the same product. But with ELBS persulfate oxidation, phenol upon oxidation with K2S2O8, K2S2O8, it is a salt of ferrosulfuric acid. Here we are getting para 1,4 dihydroxybenzene, para dihydroxybenzene. This reaction what we call ELBS persulfate oxidation. So in ELBS persulfate oxidation quite different from the remaining all. Here you are getting product 1,4 dihydroxybenzene. Students, so far we discussed named reactions of phenols. Now let us see test for phenols with a neutral FeCl3. In the beginning of the reaction we learned that. In the beginning of the session we learned that with neutral FeCl3 it gives violet color complex, and this reaction can be given by all enols but not all alcohols. Suppose ethyl alcohol cannot perform this reaction. This neutral FeCl3 test is for only enols but not for all alcohols. Similarly, with bromine in aqueous medium, we learned that white precipitate we are getting, that is 2,4,6 tribromophenol, whereas in non-polar medium like carbon disulfide or carbon tetrachloride, we are getting only ortho or para-bromophenol. Only in polar solvents, since phenol exists as a phenoxide ion which activates ring mode and excessive bromination takes place. Similarly, with phthalic anhydride, this is what we call phthalic anhydride. Phthalic anhydride upon reaction with phenol undergoes condensation with phenol in presence of concentrated H2SO4. This one is phthalic anhydride. Phthalic anhydride undergoes condensation with phenol. We are getting a phenolphthalein. Phenolphthalein, it is much familiar to us. It is an indicator which gives pink color in alkali medium. Which gives pink color in alkali medium. That is phenolphthalein. This one is phenolphthalein, also called phthalene. Phthalene test. Phenolphthalein. And very important reaction test for phenols is Lieberman-Nitroso reaction. In Lieberman-Nitroso reaction, phenol upon reaction with nitrous acid. That nitrous acid we can prepare by reaction of any NO2 and acid. The acid may be HCl or H2SO4. Here, by combining these two, we are getting HNO2 inside of the reaction. Now, phenol upon reaction with HNO2, earlier we discussed that nitrosophenol. That nitroso group comes to either ortho or para. So here para-nitrosophenol, the resonance structure one more here, it exists like this. This is a quinone form, and here para-nitrosophenol. This para-nitrosophenol resonance structure is participating in reaction with phenol, nothing but condensation. Here OH group of this para-nitrosophenol and hydrogen of phenol. Here water molecule eliminate out by whenever we are using concentrated sulfuric acid. And here we are getting OH, ring end of one, and OH plus, because of this reaction takes place in acid medium. So this is nothing but indophenol monosulfate which exists in cation form. Positive charge is there. It exists in cation form and it shows bluish green, blue-green color. Indophenol cation form, blue-green, and which upon treatment with water, this HSO4 minus comes out as H2SO4, and now only indophenol remains, which is in red color. And if further reaction with NaOH, because of here OH will be acidic, and which upon reaction with NaOH, this H plus will be abstracted and O minus remains, that O minus again involved in delocalization. We are getting indophenol anion, which is again blue color. So first paranitrosophenol upon reaction, upon condensation with phenol, we are getting indophenol. Indophenol in cation form it shows blue-green color, and which upon wash with water, we are getting only indophenol. It's not in cationic form, only indophenol, which is red in color, and indophenol upon reaction with the base, it exists in anionic form. Still again it turns to blue color. This is reaction for phenols, Lieberman-Nitroso reaction, and this is not only test for phenols but also nitro compounds.